Welcome. So this is the second derivative test for relative extrema. And it's a convenient application of the second derivative. Let f be a function such that x equals c is a critical value of f, such that f prime of c equals 0. If f double prime of x exists on an open interval containing x equals c, then, right, so just let's clarify that. If a value of x is a critical point for the first derivative, in other words, the first derivative equals 0, you find your second derivative and you're going to plug it in. Right? So you're finding the critical points for the first derivative where it's 0 or undefined, and you're testing them in the second derivative. If f double prime of c is greater than 0, then f of c, you plug it back into f, right, and to f of x to find the y value, is a relative minimum. If f double prime of c is less than 0, then f of c is a relative maximum. Right? So let's think about this. If the second derivative is positive, using the critical point for the first derivative, then it's going to be a relative minimum. Now, why would it be a relative minimum? Well, if the second derivative is positive, it's concave up. You can put this in your notes. Right? So if the second derivative is positive, it's going to be concave up. And if it's concave up, that means that that value is a minimum. Right? It's going to be down here. If the second derivative is negative, it means the function is going to be concave down. So the extreme value is going to be a maximum. Right? So second derivative positive, that value is a minimum. Second derivative negative, that value is a maximum. If the second derivative is 0, then the test fails, and the first derivative test must be used. So you need to do a sign chart. Right? So now you have two ways to find a relative extreme value. And let's take a look. And this one is in your notes. It's at the bottom of the page. And I have that, I think the two values are switched. The 2 pages are switched. The learning of, in your notes there where you see learning about functions from derivatives, that's the next page coming up. All right, so let's take a look. I'm going to find, first of all, take the first derivative and find the critical points. Right? So our first step is take the first derivative. Right, so that would be f prime of x equals 3x squared minus 6. All right, we're going to set that equal to 0 because we're going to find the critical points. So that'll be step 2, find the critical points. Now we don't have to worry about f prime of x being undefined. It's a quadratic. It's defined everywhere. So we're just going to set this equal to 0. So 0 equals 3x squared minus 6. Right? That's add 6 to both sides. We're going to solve using square roots. 6 equals 3x squared, divide by 3. So 2 equals x squared, and then take square root of both sides. And don't forget plus or minus for this side. So x is equal to plus or minus the square root of 2. Those are the critical points. Right, so x equals square root of 2 and x equals negative square root of 2. All right, so now step 3, we're going to find the second derivative. Right, so we have, my shadow keeps blocking here, f double prime of x equals 6x. All right, pretty easy derivative. We're going to take those critical points, we're going to plug them in. So f double prime of negative square root of 2 would be 6 times negative square root of 2, which is just negative 6 square roots of 2. Of course, that is negative. And let's find the other value. F double prime of square root of 2, well, that's just going to be 6 square roots of 2. Here we have a positive value. All right, so our second derivative test, we can use that, right, because we didn't get 0. And now let's analyze our function, right? What's the relative max, what's the relative min, and justify. And I'm going to put the justify up here because I don't have a whole lot of space at the bottom of the page. All right, so we have, oops, well, there goes my page. All I wanted to do was start my sentence differently. Oh, there goes my J and my U. There is a relative again, my shadow was like, oh, there's the work. We have a relative maximum at, and we know the x value is negative square roots of 2. If we want to find the y value, we'll have to plug that into the original function. So I'll kind of squeeze it in over here. F of negative square root of 2 would be, oh, of course, I don't have room over there. There we go. Let's put it right here. F of negative square root of 2 would be negative square root of 2 cubed minus 6 times negative square root of 2 plus 5. Right, that's going to be negative square root of 8. And this would be plus 6 square roots of 2 plus 5. Not a very pretty number. We could simplify this part. So this would be negative 2 square roots of 2 plus 6 square roots of 2 plus 5. So we could call that 5 plus 4 square roots of 2. So negative 2, 5 plus 4 square roots of 2. Because f double prime of negative square root of 2 is less than 0. So x equals negative square root of 2 is a relative maximum using second derivative test. And there is a relative minimum. I'm being wordy again. I'm going to run out of space. At square root of 2. All right, so I'm going to erase this. I don't have room for it. If we plug in the square root of 2, we would have f of square root of 2 is square root of 2 cubed minus 6 square roots of 2 plus 5. That's going to be 2 square roots of 2 plus 6 square roots of 2 plus 5. So that's going to be 8 square roots of 2 plus 5, or 5 plus 8 square roots of 2. Because f double prime of square root of 2 is greater than 0, making this value a relative minimum using second derivative test. There, I squeezed it in. And an abbreviation. All right, let's read through this. Make sure my sentences are reasonably unwordy. There's a relative maximum at negative square root of 2, 5 plus 4 square roots of 2, because f double prime of negative 2 is less than 0. So x equals negative square root of 2 is a relative max using the second derivative test. I could have used that space over there where I had the work before. There's a relative minimum at square root of 2, comma 5 plus 8 square roots of 2, because f double prime of 2 is greater than 0, making this value a relative minimum using the second derivative test. Right? So in other words, right here we have a relative maximum because it's concave down. Right? Because f double prime of x is less than 0. And right here we have this relative maximum because, or relative minimum, because it's concave up. F double prime of x is greater than 0. Right? So where the function's concave up, you're going to have a relative max. Where the function's concave down, excuse me, let's say that again. Where the function's concave up, you're going to have a relative min. Where the function is concave down, you're going to have a relative max. Right? So that's why when the second derivative is negative, it's a relative max. When the second derivative is positive, it's a relative min. All right? This is the visual that's in your notes. All right, so learning about functions from derivatives. All right, so y equals f of x. This is differentiable, it's smooth, it's connected, graphs rise and fall. If the first derivative is positive, the graph rises from left to right. If the, and it can be wavy, doesn't have to be a straight line. If the first derivative is negative, the graph falls from left to right. So the first derivative tells you where the original function, where y is increasing, and since it says y equals f of x, I'll put f of x. F of x is increasing here. Here, f of x is decreasing. The function's going to increase where the first derivative is positive. It's going to decrease where the first derivative is negative. If the second derivative is positive, it's concave up. All right, so, and when it says concave up, it means that f of x is concave up. If the second derivative is negative, then our function is concave down. You have inflection points where the second derivative changes signs. If the first derivative changes signs, the graph has a local max or a local min. Right? So in the first example, right, here the function was increasing, so the first derivative is positive. Here the function's decreasing, so the first derivative is negative, and there's our inflection point. Right here, the first derivative would be 0. And the same thing over here, so this would be a relative max, right, because the function changed from increasing to decreasing. This one is a max. Here we have a relative min because the function changed from increasing to decreasing. So here the first derivative is negative, then the first derivative is positive. This right here, on this point, the first derivative equals 0 because we have a relative min. You can also use the second derivative test for extrema. If the first derivative is 0 and the second derivative is negative, then the graph has a local maximum. If the first derivative is 0 and the second derivative is positive, then the graph has a local minimum. So here you have kind of everything summed up about the first and derivative test. First and derivative test looking for relative extrema. All right, so now let's try this one. This one is in your notes. Find the critical points for x cubed plus 3x squared plus 1. Use the second derivative test to classify each critical point as a relative max or min. Okay, so we find the first derivative. I'm going to try to write smaller so I don't run out of space like I did in the last slide. f prime of x equals 3x squared plus 6x. Right? Now we set that equal to 0, so we're going to find the critical points. It's defined everywhere, so we're just looking for where the first derivative is 0. So 0 equals 3x squared plus 6x. Let's factor out a greatest common factor, the 3x, and we're left with x plus 2. So if 3x is 0, x is 0. If x plus 2 is 0, x is negative 2. Now we can do what we did in the first series of videos where we did a sign chart, right? And we found the values on either side, and we looked and see whether it was increasing or decreasing to determine. Or we can use the second derivative test. Right? So the second derivative test, we find the second derivative, we plug in those critical points, and then we look at the sign. If the second derivative is positive, it's a relative min. If the second derivative is negative, it's a relative max. All right? So here in this particular video, we're using the second derivative test to classify the max and mins rather than the sign chart. You should be able to do either one of them. All right? So let's find the second derivative, and we'll evaluate the critical points from the first derivative. All right, so second derivative is f double prime of x equals 6x plus 6. All right, so we have f double prime of 0 would be 6 times 0 plus 6. So that's 6. So this one here is a relative minimum because it's positive. And then we have the second one was the negative 2. So f double prime of negative 2 would be 6 times negative 2 plus 6, and that's negative 6. So this is going to be a relative max. And now let's justify. Right? So I'm going to see if I can be more succinct than I was in the last slide. You never know when I start writing. Using the second derivative test, but it really doesn't matter how succinct you are as long as you have the information you need and it's correctly justified. So using the second derivative test, 0, and if we plug that back in, it would be 1. 0, 1 is a relative minimum. Because f double prime of 0 is greater than, so it's a relative minimum because it's positive, it's greater than 0. Keep forgetting what the values are because my shadow keeps blocking. So using the second derivative test, 0, 1 is a relative minimum because the second derivative is greater than 0. And negative 2. Negative 2, and if we plug that back in, that would be negative 2 cubed would be negative 8. And then, just squeeze it right here so I can remember the numbers. Negative 2 cubed would be negative 8. And then 3 times negative 2 squared is going to be 12. So that would be negative 8 plus 12 is 4, plus 1 is 5. So negative 2, 5 is a relative maximum because f double prime of negative 2 is less than 0. I think I said that much more succinctly. Should change the other one. Right? So I put using the second derivative test first, so I only had to say it one time. Right? So I just made this one sentence this time. I said that really nicely. Using the second derivative test, 0, 1 is a relative minimum because f double prime of 0 is greater than 0. And negative 2, 5 is a relative maximum because f double prime negative 2 is less than 0. Right? So concave up, going to be a relative max. Relative min. Concave down is going to be a relative max. All right, here's the next one. And this one is in your notes. We just didn't, for some reason, the function's not written down. The first derivative of a certain function f of x is f prime of x equals x squared minus 2x minus 8. A, find the intervals on which it is increasing and decreasing. Find the intervals of the graph of f is concave up, concave down. Find the x-coordinate of the relative extrema and the inflection points of f. Okay? And we can use the first derivative test or the second derivative test to answer A. Let's do the first derivative test for A and the second derivative test for C. That we get a little practice for both. All right, so we already have the derivative. All right, so for A, we're going to set that equal to 0. We're going to find the critical points, which we'd have to do no matter which test we used. So it says 0 equals, because it's not undefined anywhere, and this factors to x minus 4, x plus 2. So x minus 4 is 0, x is 4, and x plus 2 is 0, x is negative 2. These are the critical points. Let's do a sign chart to look at where it's increasing and decreasing. All right, so we have negative 2, that's a 0. 4 is a 0. We'll plug in, oh, not 3. 3 is okay, but 0 is the best. And then negative 3 and 5. All right, so, and we're plugging them into the first derivative. So f of negative 3 would be negative 3 squared minus 2 times negative 3 minus 8. That's going to be 9 plus 6. 15 minus 8, that's 7. That's positive. That's all we really care about. F of 0 is negative 8. That's negative. And f of 5 is 5 squared minus 2 times 5 minus 8. That's 25 minus 10. So that's going to be 15 minus 8. That's 7. That's going to be positive. All right, so f of x is increasing on negative infinity. So my infinity doesn't look very good. Negative infinity to negative 2. And 4 to infinity, because f prime of x is greater than 0 on these intervals. Or on this interval would be fine too. F of x is decreasing. So notice I never use pronouns. I always say the name of the function, f of x, f prime of x, first derivative. You got to be specific, all right? So f of x, the original function, is decreasing on negative 2 to 4 because f prime of x is less than 0 on this interval. All right, so we've answered A. Now let's answer B, the intervals on which the graph of f is concave up, concave down. So we need the second derivative test. Or second derivative, excuse me. Just the second derivative. And that would be f double prime of x is 2x minus 2. Right? And then we'll find the critical points. So we found the second derivative, we took the second derivative, now we're going to find the critical points. So this would be 0 equals 2x minus 2. So 2 equals 2x and x equals 1 is the critical point. Right? So 1 is our only critical point, so we're going to plug in something less than 1, like 0, and something more than 1, like 2, into the second derivative. Right? And I think we can just do this in our head. Right? Plug in 0, we get negative 2. That's negative. If we plug in 2, we get 2. That's positive. Right? So that means that f of x is concave down on negative infinity to 1 because f double prime of x is less than 0 on this interval. I need more space. There we go. F of x is concave up on 1 to infinity because f double prime of x is greater than 0 on this interval. There we go. So we have identified increasing, decreasing. We've identified concave up, concave down. Now we need the x-coordinates. If this just says x-coordinate, we don't need the whole point. For the relative extrema and the inflection points. All right. So we already know one of those. Right? We know it from the sign chart. We know our relative extrema. We know our inflection point. And we can also identify from the sign chart for the first derivative the relative extrema. All right? Maybe we'll just do a double check. Right? So x equals negative 2 is a relative max because f prime of x changes sign from positive to negative. And let's justify it again. Using the second derivative test, f double prime of negative 2. So f double prime of negative 2, if we plug that in, that would be 2 times negative 2. Negative 4 minus 2 is negative 6. Okay, so using the second derivative test, f prime of negative 2 equals negative 6. Since f double prime of x is less than 0, is that in there? F of negative 2, or x equals negative 2 is a relative maximum. Oh, can we squeeze in the last part? X equals 4 is a relative min because f prime of x changes sign from negative to positive. And I should say here, I'm going to squeeze that in, at x equals, even like I said, it's going to be a big old mess. I was watching the recording wasn't moving. So I think maybe the whole thing was paused. Here, let's just write it again. Here, let's just cut that, and I'll write that nicer. And erase. Okay. X equals negative 2. Such much work for a little at x equals. All right, so the x equals 4 is a relative min because f prime of x changes sign from negative to positive. Just abbreviate at x equals 4 using the second derivative test. Just get a little bit more space. got to work on my spacing here. That'll be a goal for me. So using the second derivative test, f double prime of 4, that would be 8 minus 2 would be 6. So I can make this a short sentence. Using the second derivative test, f double prime of 4 equals 6. Since f double prime of 4 is greater than 0, x equals 4 is a relative min. There we go. We squeezed it in. It's not written very nicely. Maybe I can, before I post this, can work on this. But we have all the information in there. There we go. Hopefully you can read it. There we go. I think that's as good as it's going to look. All right. So that's all there is to these. All right. And if I have more space, I think it would even look a little clearer. We found, oh, we didn't find one thing. One thing. The inflection point. Let's put that down here with the concavity. So here's C part 2. X equals 1 is an inflection point because the second derivative changes sign at x equals 1. There we go. Now we have everything in. And now we are done with this one. We've identified increasing, decreasing, concave up, concave down, relative max and min using 2 methods, not just one, and have identified the inflection point. Quick little review. Second derivative test, if f prime of c is 0 and f double prime of c is positive, then f has a relative minimum at c. If f prime of c is 0 and f double prime of c is negative, then f has a relative maximum at c. Right, so just think, positive minimum, negative maximum. If f prime of c equals 0 and f double prime of c equals 0, then the second derivative test is inconclusive and use the first derivative test instead. Right? So second derivative for concavity. So we have a second derivative test for Extrema. This one was for Extrema. And we have a second derivative test for concavity. It's concave up, where y double prime or f double prime of x is greater than 0. Concave down, where y prime or f double prime of x is less than 0. If f double prime of c equals 0, it's a possible inflection point. If f double prime of c changes sign from positive to negative, or negative, or vice versa. Then C is an inflection point. You're looking for a change in sign. If there's a change in sign, there's a change in inflection, change in concavity, then that value is an inflection point. Right? So the critical point for the second derivative is a inflection point if there's a change in concavity. And that occurs where there's a change in sign for the second derivative. All right, so this is in your notes, just a little summary here. And you can use this to help you out, and it includes how you can change this into a justification on the next slide. All right, so if the first derivative is positive, so if y prime is positive, then y is increasing. If y prime is negative, then y is decreasing. If y prime changes from negative to positive, then y has a local minimum at that value. If y prime changes from positive to negative, then y has a local maximum at that value. If y prime is increasing and y double prime is greater than 0, y is concave up. If y prime is decreasing, y double prime is less than 0, y is concave down. Those extreme values for y prime end up being critical values for y double prime, and those are going to be our inflection points. And it's going to be where y double prime, where the second derivative changes signs. And so, since justify your answer is often part of the question, turning the table around provides for your justification. So y is increasing where the first derivative is positive. Y is decreasing where the first derivative is negative. Y has a local minimum where the first derivative changes from negative to positive. That would be the first derivative test. Or, if you're using the second derivative test, you can add this to your notes. Y double prime is positive. Actually, let's put, instead of the word is, that's right, that way. Right? And so that would be the second derivative test. Y has a local maximum where the first derivative changes from positive to negative using the first derivative test, or where the second derivative is negative using the second derivative test. Y is concave up where the first derivative is increasing, or the second derivative is greater than 0. Y is concave down where the first derivative is decreasing, or the second derivative is less than 0. And y has points of inflection where the first derivative has extreme values, or the second derivative changes sign. All right, add those parts to your notes, right, to make them a little bit more complete, so you have more than one way, to as many ways as possible, to justify your answers and to find those critical points, those relative max and mins, and inflection points for your function. And that, I thought, was my last slide, and I was right. All right, so be looking for a closing, so you can respond to some questions on this. It might be an online closing, but you'll know that. I will send you that information. And this is the end of the second derivative test. In the next videos, we'll be looking at curve sketching and analyzing the derivatives from a function, or the function from the derivatives, all kinds of good fun. All right, bye for now.